So in this video, the problem we want to solve is the following. Suppose we have 2 points in the xy plane. We have a point M with coordinates 0 and A, so this lies on the y-axis, and a point N, which has an x-coordinate of H and a height y-coordinate of B. And we want to find a point P on the x-axis such that the length of MP plus Pn is minimum. So x can be any point along the x-axis, and we want to find the specific point in which this the sum of these two lengths MP plus Pn equals minimum. So how can we do that? So the length Mn, I've called it here, equals L1. So let's draw this triangle again. So I have a triangle. The hypotenuse is equal to L1, and this is the point M, and this is the point P, and this point is the origin. The coordinates of P are x, so this distance here is x, and then M has a y coordinate of A, so this height is equal to A. So the length of L1 is equal to the square root of A squared plus x squared. So let's look at the other triangle. So the triangle formed by P, N, and this point here. And let's redraw that triangle. So the height, so this is our point N, and this is our point P. This has, the point N has a height of B, so the height of this triangle is B, and we've called the hypotenuse L2, and this is a right angle triangle. This point, which corresponds to this point here, has an x coordinate of H, while this point has an x coordinate of X. So the length of this segment here is H minus X. So that's the length of the distance from P all the way to the projection of N onto the x-axis. So similarly, we have a right angle triangle. L2 is the hypotenuse, so L2 equals to the square root of B squared plus H minus X squared. So let's call the length that we're trying to minimize L of X. So L of X is MP plus Pn, which is equal to L1 plus L2, which equals to the square root of A squared plus X squared plus L2, which is B squared plus H minus X squared. So we want to find the value of X that causes L of X to be minimum. So how are we going to do that? So we're going to do that through differentiation. So let's do a plot here. So this is the x-axis, and well, actually, yeah, this is the length of X. We have L as a function of X. L here is only a function of X. A is constant, B is constant, H is constant. So we have the length as a function of the X value. And if you think, if we move X here all the way, let's say far to the left, L will have a certain distance, and as you bring it in closer, the sum of L1 plus L2, just by looking at it, is expected to decrease. And then if you move X all the way far to the far right, then the length of L1 plus L2 is expected to increase. So L as a function of X will look something like this. So it's going to start as a big value, it's going to decrease, and it's going to rise again. Somewhere here along in this region here, L of X will become minimum. And at that specific point, the tangent to the function will have a slope of 0. So at the minimum of L of X, we have this property that dL of X by dx equals to 0. Remember, the derivative of L with respect to X has a geometric meaning, which is it's the slope of the function at the point at which you're computing this derivative. So at this point, if we were to draw a tangent to the function, so dl of x by dx would be the slope of this line at this point here. And at this point here, dl of x by dx would be the slope of the line at this point here. At the minimum, the line, the tangent to the curve, is actually horizontal and has a slope of 0. And so the key to finding the minimum of L of x is to get the derivative of x, L with respect to x, and to set it equal to 0. So let's do that here. So, and just before we do that, let me remind you, if we have y equals to the square root of x, which is equal to x to the 1/2, then dy by dx equals to x to the 1/2 is equal to minus half, and then we subtract 1 from the power, so it's it's x to the 1/2 minus 1, which equals minus 1/2, x to the minus 1/2, which equals to, sorry, this should be a plus sign here. This should be plus. So that equals 1 over 2 square root of x. So the derivative of square root of x is 1 over 2 square root of x. So let's get back to L of x. So dL of x plus dL of x by dx equals, we want to get the derivative of this term plus the derivative of the second term. So square root of a squared plus x squared, that equals 1 over 2 square root of a squared plus x squared. That's the rule that we just said here. Plus we need to take the derivative of what's inside the square root. So the derivative of a squared equal to 0 because it's a constant. The derivative of x squared is equal to 2x. So that's the derivative of the first term. Similarly, the derivative of the second term is 1 over 2 the square root b squared plus h minus x squared, plus the derivative of what's inside the square root. The derivative of b squared is equal to 0. The derivative of h minus x squared is 2h minus x times the derivative of minus x is minus 1. So now we need to set dL of x by dx equal to 0. So first of all, this 2 will cancel with this 2. This 2 will cancel out with this 2. So we have x over square root of a squared plus x squared equals to h minus x divided by square root of, this should have been minus, divided by b squared plus h minus x squared. The left-hand term here, we're setting it equal to 0. So that means x divided by square root of a squared plus x squared equals to h minus x divided by b squared plus h minus x squared. And let's call this equation 1. Now, before we move on, x divided by a squared, square root of a squared plus x squared. This square root is equal to L1. So equation 1 could have been written as x divided by L1 equals to h minus x divided by L2. So this denominator here equals to L2. So that's a different way of writing equation 1, and it has an important geometric property. So if you look at this triangle here, x divided by L1. X is this distance here, divided by L1, that's the cosine of this angle here. If you call this angle here theta 1, and let's call this angle here theta 2. So equation 1 is telling us that cosine theta 1 equals cosine theta 2, which means that theta 1 equals to theta 2. So this is an important geometric property, and we'll come back to it later. So let's move on. So we want to find the value of x. So let's square equation 1. So square 1. That gives us x squared. So I'm going to do 2 steps. I'm going to square it and I'm going to flip the terms upside down. So the denominator becomes the numerator, and you'll see why in a second. So if we square the square root of a squared plus x squared, we'll have a squared plus x squared divided by the square of the numerator becomes x squared equals, we're going to flip this term as well. It's going to be b squared plus h minus x squared divided by h minus x squared. Now this can be simplified as a squared plus x squared divided by x squared is a squared over x squared plus 1 equals b squared over h minus x squared plus the 1. The 1 cancels with the 1. Now everything here has a square to it, so we're going to take the square root of that. So a over x equals b over h minus x. And let's swap these two terms, a and h minus x. Therefore, h minus x over x equals b over a. Therefore, h over x minus 1 equals b over a. Therefore, h over x equals 1 plus b over a. And then we'll swap x. We'll make this term the denominator. So swap x and this term here. So that means x equals, equals h divided by 1 plus b over a. So this is the value of x. And as I said, let's assume b equals to a. Let's say b and a had the same height. So I'll just draw this up here because I ran out of space. So let's see, this is a and this is b, and these 2 points had the same height. Well, we said that the final solution will have these 2 angles being equal. And the way that can only happen with b equals to a is if h falls right exactly in between these 2 points here on the x-axis. So this point here has to equal h over 2. In order for these 2 angles, theta 1 and theta 2, to be equal, this point here on the x-axis has to lie halfway in between. And we can see here, if a equals b, x equals to h over 1 plus 1, which equals to h over 2. So the solution has a nice geometric property, and it's the following. If you think of the x-axis as a mirror, and you were to shine a beam of light from A, and it would hit the point at which we are claiming the length here is minimum, the light is going to reflect back all the way and hit back our point N. So the solution to this problem has this nice geometric property, and if we erect here a perpendicular, let's try and do this once more. So assuming this was a perpendicular, so if you shine a beam of light here, the angle of incidence, let's call this alpha, with the perpendicular equals the angle of reflection, which is alpha 2. So the beam of light would fall down here, hit our point X, and it would reflect back and go through our point N. So the final solution to our problem is x equals h over 1 plus b over a.